Good morning, students. I am Dr. Shubha, Assistant Professor in Chemistry, Government PG College for Women, Sector 14, Panchkula. Topic for today's presentation is Vibrational Spectroscopy. Vibrational spectroscopy. These spectra arises when the absorbed energy causes transitions between various vibrational energy levels of a molecule within the same electronic energy levels. The excitations occur in both rotational and vibrational energy levels. This energy is available in infrared region. So that's why it is also called infrared spectroscopy. IR spectra is observed when the vibrational motion of a molecule is accompanied by a change in dipole moment of the molecule. Infrared spectroscopy or the vibrational spectroscopy is the measurement of the interaction of the infrared radiation with matter by absorption, emission, or reflection. It is used to study and identify chemical substances or functional groups in solid, liquid, or gaseous forms. Vibrational spectroscopy is also called infrared spectroscopy. So these are the infrared region ranges. Near infrared region, the range is 12,500 to 4,000 centimeter inverse. Middle infrared region 4,000 to 667 centimeter inverse. And for the far infrared region, the range is 667 to 50 centimeter inverse. Types of molecules which exhibit vibrational spectra. The gross selection rule for a molecule to show vibrational spectrum is that the vibrational motion of the molecule must be accompanied by a change in dipole moment of the molecule. An oscillating electric field from a molecule is generated only when its vibration causes a change in dipole moment of the molecule. The oscillating electric field of the molecule interacts with the electric field of radiation and the molecule undergoes transition from a lower vibrational length to higher vibrational level. The molecule need not possess a permanent dipole moment. Homonuclear diatomic molecules have zero dipole moment. So there is no change in dipole moment when the molecule undergoes vibrations. Hence the molecules like hydrogen, oxygen, nitrogen do not give vibrational spectra, and these molecules are said to be infrared inactive. Now the heteronuclear diatomic molecules, for example HCl, HF and carbon monoxide, and other polyatomic molecules like carbon dioxide, water, ammonia, ethene, etc., which exhibit change in dipole moment in some of their vibrational modes are infrared and hence they give vibrational spectra. So the infrared active molecules are HCl, HCN, and in polyatomic molecules like water, CO2, ammonia, methane, etc. Examples of infrared inactive molecules are hydrogen, chlorine, nitrogen, which are symmetrical diatomic molecules. And the bond stretching vibration doesn't result in any change in the dipole moment, so they do not show infrared spectra. Now the expression for vibrational energies of simple harmonic oscillator. A simple harmonic oscillator is a particle which oscillates about an equilibrium position, which is taken as origin and is acted upon by a restoring force which is denoted by small f, whose magnitude increases linearly with displacement x from the equilibrium position. So in such oscillator, when the particle is displaced from its equilibrium position, the restoring force starts acting on it in the opposite direction so that in order to restore to its equilibrium position. The restoring force, the small f, is equal to minus kx, and here k is the proportionality constant. It is also called force constant, and x is the displacement. The minus sign here denotes that force acts in the direction opposite to the direction of displacement. So this equation is also known as Hooke's law. The potential energy of such an oscillator over the distance at which the force acts is given as V, which is potential energy, is equal to minus F dx. So we will get half kx square. This equation shows that the oscillator can have any positive value of potential energy. Therefore, this equation is the equation of parabola, as we can see in this figure. So when the potential energy V is plotted against the displacement from the equilibrium position, a parabola is obtained, as we can see in the lower figure. The vibrational frequency of the simple harmonic oscillator having mass m is given as mu is equal to 1 upon 2 pi under root k upon m. Where mu is the reduced mass of the diatomic molecule, and here m1 and m2 are the masses of atoms which are connected by a spring. The solution of Schrödinger wave equation for a simple harmonic oscillator gives the quantized vibrational energy levels as E mu is equal to mu plus half h mu. Here mu is the vibrational quantum number and h mu, that mu is the vibrational frequency. Thus, the energy levels of a simple harmonic oscillators are equally spaced, and this is also shown in the middle figure. So, it should be noted that the lowest vibrational energy, which is obtained by putting the vibrational quantum number is equal to 0, we get E mu is equal to half h mu joules. And this implies that molecule can have never zero vibrational energy. So the quantity half h mu is called the 0 point energy. Vibrational spectrum of diatomic vibrator. Applying selection rule delta mu is equal to plus 1, the energy absorbed for a transition take place from mu to mu plus 1 vibrational level is given by this equation, and we get omega e centimeter inverse. A simple result can be derived from this equation, that is, all vibrational levels are equally spaced with a spacing equal to omega e centimeter inverse. Therefore, the transition between any two neighboring energy levels will appear at the same wave number. Thus, the vibrational spectrum of a molecule will contain only one absorption line appearing at the wave number equal to equilibrium vibrational frequency of the diatomic molecule. Further, at the room temperature, most of the molecules are present in ground vibrational level, whereas the populations in the higher levels are comparatively negligible. So the most intense transition is that which takes place from mu 0 to mu 1. The vibrational frequency corresponding to this excitation is the fundamental frequency. Now the selection rule for the vibrational spectrum transitions. The Gross selection rule is that for vibrational transition to occur, the vibration must involve a change in the dipole moment of the molecule. Thus, vibrational spectra will be observed only in heteronuclear diatomic molecules, since homonuclear diatomic molecules have no dipole moment. The specific selection rule for a simple harmonic oscillator is delta mu is equal to plus minus 1. That is, during a vibrational transition, the vibrational quantum number mu can change by 1. Delta mu plus 1 refers to absorption, and while the negative 1 refers to emission. Now, the application of infrared spectroscopy. So, the structural information from infrared spectra. So, we can also calculate moment of inertia and the bond length. In the rotational spectrum, the frequency separation delta mu is also known from the spectra. So, delta mu bar is equal to 2b centimeter inverse. So, the other application is that we can calculate the force constant. As I have already discussed, the diatomic molecule vibrating as simple harmonic oscillator obeys Hooke's law, according to which the restoring force is directly proportional to displacement x, where x is the displacement is equal to r minus re. Hence, r is the distance to which atoms have been stretched, and re is the equilibrium distance between two atoms, and F is the force constant. When x is equal to 1 centimeter, K is equal to minus F. The force constant is defined as the restoring force per unit displacement of simple harmonic oscillator. The force constant and vibrational frequency of a harmonic oscillator are related as omega E is equal to 1.2 pi under root K upon mu. So on the rearrangement, it gives that K is equal to 4 pi square omega E square mu, and we know that mu is the reduced mass. The value of omega E can be determined from fundamental absorption corresponding to transition mu is equal to 0 to mu into 1, and the first overtone corresponding to transition between mu is equal to 0 to mu is equal to 2. Substituting the value of omega E m1 and m2, the value of force constant can be calculated. The unit of force constants are dyne per centimeter inverse in CGS system and Newton per meter inverse in SI system. Each bond has a different value of force constant. The value of force constant reflects the bond strength of a bond. So force constants are the bond lengths of some diatomic molecules, which we can see in this table. So it is clear from this table that as the force constant increases, the bond distance decreases. Further, the bond energy is inversely proportional to bond length. So this table also reflects the bond energy of the halogen acids as HF is greater than HCl, greater than HBI, and greater than HI. Force constant increases with the multiplicity of the bond. The force constant and hence bond energy for single, double, and triple bonds follows the order. K C triple bond C is greater than force constant of double bond, and hence it is greater than force constant of single bond. Now the vibrational frequency of different functional groups. A complex molecule will exhibit normal modes of vibration as per 3n-6 and 3n-5 rules. These vibrations may involve some or all the atoms in the molecule. The magnitude of displacement will be different for different atoms or groups present in the molecule. In the infrared spectrum of a molecule, normal modes can be divided into two classes. The first is the skeletal vibration, which involves all the atoms to almost the same tent. And other one is the group vibration, which involve only small group of atoms that undergoes vibration compared to the rest of the molecule. A particular functional group has characteristic vibrational wave numbers and intensities of the peaks. The skeletal vibrations occur in the range of 1500 to 700 centimeter inverse, while the group frequency are almost independent of the structure of the molecule as a whole and fall in the regions well above and well below that of the skeletal modes. The resulting whole molecule region of the absorption spectrum is called a fingerprint region of the spectrum, since it is a characteristic of a molecule. The wave numbers of some functional groups are listed in this table. These are the characteristic infrared absorption frequency for some functional groups. As we can see, for the alcoholic group, it is 3600, and for the triple bond, this is 3300. So similarly, for the ketone group, it is 1750 to 1600. So these are some trends. The trends of group frequency can be explained in the accordance with this equation. Omega E is equal to 1 upon 2 pi under root k upon mu joules. It is clear from this table that within a group, increase reduced mass, that is mu, decreases with frequency of the series CH, CF, CCl and CBr. We can see that the frequency of this CH is different than CF, which is 1050, and for the CCl it is 725, and CBr is 650, and CI further decreases to 550. Also, the increasing strength of the bond and hence increasing the force constant K tends to increase the frequency. Example in the series single bond, double bond and triple bond. The order of force constant is triple bond force constant is greater than double bond, and which is greater than the single bond. So same is the order of absorption frequency in which these groups appear in the spectrum. Thank you.